good afternoon. My name is Mark Kudek. I'd like to welcome you to the panel, Spectrum Above 100 Gigahertz, a reality check. It is sponsored by the mmWave Coalition. I will be your moderator today. I am also the chair of the mmWave Coalition. The focus today is going to be on sub-terahertz, looking at all the improvements for 6G and sub-terahertz being one of those key enablers. And there's been a lot of work in that area, and we have some very distinguished panelists with us today. I'm going to briefly introduce them, and I'll let them share a bit more about themselves as they go on. Today we have 7 panelists. We have Amitava Ghosh, who is a Nokia fellow from the strategy organization at Nokia Corporation. We have Ozge Koyman, who's the senior director at Qualcomm. Michael Marcus, who is a policy specialist in spectrum policy at Marcus Spectrum Solutions. We have Dan Middleton, who is a professor at Brown University. We have Roger Nichols, a senior strategic director at Keysight. We have Ted Rappaport, a professor and founder of NYU Wireless Research. And then we have Gerhold Schoenthal, a COO at Virginia Diodes. So what we're going to do here is we're going to have an interactive panel. I invite questions from the audience to come in the chat, but we're going to start off this meeting with some questions to the panel and let them introduce each themselves. So the question that I'm going to pose to all the panelists today are, given what you've learned in the past few years on propagation, device capability, that's the next question. What is your opinion on the most critical aspect that needs to be addressed to make communications above 100 gigahertz a reality for 6G? And I will let Amitava kick that off.
You're muted, Amitava.
Okay, that's a good question. I think what we have to look, what are the main use cases for sub-terahertz? And that's one of the key questions we need to answer before the sub-terahertz becomes useful. What we have seen that millimeter wave up to 28 gigahertz, 39 gigahertz, 47 gigahertz was introduced, up to 52.6 gigahertz was introduced in release 15 NR, but it has not taken off. There are some deployments with fixed wireless access, but densification has not happened. It has not taken up because you need these bands for capacity. And so does sub-terahertz, because there may be other uses in sub-terahertz like imaging, sensing, etc. But the main thing we have to identify, what are the main use cases in this band?
Okay, thank you, Amitava. And with that, I'm going to go in alphabetical order here. So we're going to go to Ozge Koyman with Qualcomm next.
Hi, good afternoon, everyone. My name is Ozge Koyman. I lead the millimeter wave project in Qualcomm Research. I think sub-terahertz is still in an exploratory stage, I think, for many of us, both from a device side, from a use case side, and just to see where it really fits in, because we do have substantial work on FR2, and FR2 deployments have not really taken off that much. But I do feel like a lot of the components we're building in FR2 to enable FR2 in terms of the nodes for densification, the progress we've made, will also be important for sub-terahertz. So depending on the use case, whether it's fixed point-to-point links or a mobilized sub-terahertz where that requires power efficient, thermal efficient devices, we have different barriers for each of those. So use case is an important thing, as Amitava said. But I do feel that we're building a lot of foundations through FR2 for sub-terahertz.
Okay, thank you. Then we'll move on to Mike Marcus.
Hi. The interesting about sub-terahertz is that part of the spectrum has a very high density of passive spectrum uses, not because anyone threw darts at a dartboard, but because there are more atomic resonances up there. So if you want more than 12.5 gigahertz contiguous spectrum, and the reason why you go above 100 gigahertz is to get big hunks of spectrum for broadband modulation and efficient technology, you have to find a way to share with some of the passive users. While under 50 gigahertz, such sharing is probably impossible. These special physics of radio propagation above 100 gigahertz combined with the small wavelength that enables you to use different antenna technology than you can use lower bands makes it plausible. But unfortunately, we've never been able to get a good dialogue going between the communication community and the passive community to get a real dialogue of, can we build systems that protect the passive systems and achieve something useful? Probably impossible under 50 gigahertz, likely possible above 100 gigahertz, but the government hasn't shown much leadership, and the passive community hasn't been willing to engage. So we have to find a way to get the two sides to work together to come up with sharing solutions that are truly win-win sharing solutions. Thank you.
Good. Thank you, Mike. Then we'll move on to Dan Middleton from Brown University. Dan?
Hi, everybody. Yeah. So as a faculty, my perspective on this comes informed by sort of the research needs and the research community's activities. And from my perspective, I think there are an awful lot of interesting research challenges that need to be addressed, but there doesn't seem to be any fundamental reason why this can't work. And so therefore, I would essentially agree with a lot of what's been said already, which is that the primary need in order to make this a reality is to justify to the people who have the money that this is worth spending money on. And that means both the people who fund research and also the people who build systems. So use cases are maybe critical. I think I would also echo what Mike said, which is that, and I think many people in the research community don't appreciate the importance of this issue to the extent that perhaps they should, which is that if we don't have an ongoing dialogue with passive users, then all the work we've been doing on this topic over the past N years is going to be for naught. So I'm repeating what other people have already said.
Okay. Great. Thanks, Dan. Then we'll move on to Roger Nichols with Keysight.
Yeah, I'm a little bit more optimistic on the use case area. I think the profit-bearing use cases will evolve over time. And as Ozga said, it will evolve out of what's happening already in the FR2 space with the addition of some of the other cool things you can do above 100 gigahertz. So I actually think the most important aspect we have to address is power consumption, not just in the radio, in the the analog parts, but also in managing these amazing data rates that we would expect to get from this area. And the DSP to manage this is a big deal. I think the prevailing wisdom, I haven't seen numbers on this yet, but the prevailing wisdom is that 5G is more efficient on an energy perspective than 4G is on a joules per bit perspective. The problem is that we're using so many more bits that we haven't moved far enough in the joules per bit area. And if you talk to mobile operators, I don't have proof of this, but at least the anecdotes I've heard is the #1 corporate user of energy in the United States is AT&T, and #2 is Verizon. So that's their job is to spray energy around in the atmosphere, right? So they're going to use some anyway, but making that more efficient is going to become absolutely necessary for the sake of our environment, but also just to make it affordable.
Okay. And then we'll move on to Ted Rappaport of NYU Wireless.
Hello, everyone. It's great to see everyone on the panel and out there watching. I think we haven't seen millimeter wave FR2 take off the way you want it to, Amitabha, for a couple of reasons. #1 is COVID, and #2 is the densification requires legislation and cities to allow the smaller poles and deployment. And that's a fight that happens in City Hall around the country. The FCC tried to help that with the 2018 Small Cell Act, and the CapEx is coming. But the bottom line is, it doesn't matter what frequency, millimeter wave or 1.8 gigahertz or 2.3 gigahertz, as we get wider bandwidth channels, you have to get the access point closer to the mobile for the thermal noise. And the channel really isn't that different all the way up to sub-terahertz. The path loss is very comparable. You get a little less multipath, but measurements show that when you use double directional channels, directional antennas at the mobile and the base, you more than make up the perceived myth of sub-terahertz loss. Yeah, rain hurts you and penetration's tougher, but the bottom line is densification is going to come for mid-band. I think Nokia just announced 3 channels of 100 megahertz carrier aggregation this week and 4 gigabits per second on 5G new radio at mid-band, you know, a few gigahertz of spectrum. Well, that wider bandwidth by definition requires the access points closer for the desired signal to noise ratio. So densification is going to come, and millimeter wave is going to be just like everything else in a few years from now. And there's nothing stopping us going all the way up to several hundred gigahertz carrier. But the one thing I think we need is spectrum harmonization. We need some sub-terahertz band to become the standard by which someone can make Wi-Fi chips and know that they sell them into multiple markets. 140 gigahertz range kind of looks like that hot spot. Ofcom has to make up their policy. FCC took a step in 2019. So I think we need some of these unlicensed bands first to seed the investment and a global market that can go into laptops and cell phones that will then bring the cellular industry to a similar range of frequencies.
Okay, thanks, Ted. And then our last panelist, Gero Schoenthal from Virginia Diodes, please.
Yeah, so I think that the most critical aspect that needs to be addressed is ecosystem development. We know that the test capability for sub-terahertz is here. That's been demonstrated by multiple test and measurement type organizations. There's prototypes that are in the field in laboratories being used to show the communications can be done above 100 gigahertz. And there's tons of university and corporate research that's being done on this matter. But it's going to take a good decade for us to spin up the ecosystem, including IC fabrication, packaging, development of CPEs and UEs for specifically carrier frequencies above 100 gigahertz. There's some ways that the communications is all the same, but certainly when you get above 100 gigahertz on a very discrete semiconductor level, parasitics and those types of things start coming more in play. And so it's really important that we continue the research on all of the aspects of the ecosystem so that in the next decade, they can come together to create devices like CPEs and UEs and base stations, et cetera.
Okay, thank you. Thank you for bringing what your most critical aspect of sub-terahertz is. And so now Christina, just a question for you. Will I see the questions in the panel here? Because I don't see any yet.
So there should be in your view Q&A. I don't see any questions coming in from the attendees.
Okay. Okay. Well, let me start off with at least 2 questions from the top here. And what I'm gonna try and do here is I won't direct it necessarily to anyone unless I don't hear from you, but the first question is gonna come for use cases. So we've talked a little bit about use cases in your introductions, but when you look at the propagation, the device capabilities, some of the power consumptions, what do those use cases at sub-terahertz look like to you? Are they going to be the same ones we see down at FR2? Are there going to be new ones? are there going to be, things we haven't even thought of yet? Who would like to volunteer to take that one?
Yeah, I can take it. So thanks for that question. I think the most important use case, which is a no-brainer, is for the backhaul, right? So because for densification, you need backhaul. You can have various kinds of backhaul like IAB, like you can have smart repeaters, or you can have a separate backhaul. So the separate backhaul may be attractive at 140 gigahertz. So that is a no-brainer where you can have the backhaul and the propagation conditions are more conducive for backhaul. Now, coming back to sensing plus communication plus positioning, that may be the other use case, which will go into 6G, but not for 5G or 5G advanced. So those are the main use cases. And I like to address Ted's comment on C-band deployment. For the C-band deployment, that has been very popular. And we are reusing the macro sites. And we are getting the same coverage and capacity by just using the number of antennas to 64 TRX, you see. So you'll have the same coverage, higher coverage capacity using 100 megahertz bandwidth, but you're using the existing macro sites.
Okay, thanks, Amitava. Mike, you had your hand up. Did you want to add anything? Mike, you're muted.
Most people would say that backhaul today is primarily done with fiber, and why not continue that in the future? And the problem is that as 6G gets fielded, the backhaul demands will be bigger and bigger and bigger. And today, and in the future, you can't put fiber everywhere, because there are some places where fiber installation is extremely expensive, or is too time consuming for a special event, or is too time consuming for emergency restoration. So a 6G network can't depend upon today's radio systems for backhaul in those cases, because they don't have enough capacity. So probably the most immediate use of above 100 gigahertz will be for backhaul. I think mobile links will eventually come, but in the near term, backhaul is most important. And the other uses, non-communications uses that Dan has been a pioneer of, the terahertz spectroscopy or short-range sensing of a few centimeters, but it's like ultra-wideband on steroids, but it needs a lot of contiguous bandwidth. But this is important for quality control in many manufacturing industries, and this administration's and the Commerce Department's highest priority is to improve US manufacturing, and gadgets that help improve manufacturing efficiency through real-time quality control are also important. So there are both communications uses and non-communications uses, although this audience is probably mainly interested in the communications uses.
Okay, thanks, Mike. So are there any other use cases that Amitava or Mike hadn't addressed you'd like to add?
Yeah, so I'd say that in 5G, I think we're seeing a possible crossover between wireline and fixed wireless access for broadcast of internet, not just for mobile devices, but also for in-home broadcast. And we're a good, 10 years away from the midst of 6G deployment. And so I can envision that when we get into the mid-2030s timeframe, there'd be a solid use case for something in between maybe fixed wireless access and nomadic access of the internet. Say in a private 6G network in a large office space where you've got a tablet or a laptop computer that you need tons of data going to. And that's a bit different space than we're in today, and I think a bit different use application.
Okay.
Yeah, people talk about the ubiquitous deployment of virtual reality and things like this. That's much easier to envision when you have high bandwidth wireless connections, for sure.
And this cell phone itself is going to have very powerful phased array antennas, very short time, high bandwidth data capability. So it'll become a radar. It'll do see in the dark imaging. We'll see on the phone, like we use our phone today for a camera, we'll use it for imaging in dark areas where the wireless RF is used instead of optical. And there'll be myriad new applications with that high capacity deployment that just like we couldn't envision Uber or YouTube being delivered. Right. We'll have television and video and gaming and 3D immersive because of the bandwidth.
I think Ted makes a very important point, which is, 25 years ago, we never would have thought about streaming cat videos to our pockets. And now everyone is streaming cat videos to their pockets. So, there's going to be an awful lot of things that come along that we haven't thought about yet.
Yeah, I would leverage those in two areas. We're just starting to scratch the surface on industrial IoT use cases for 5G. There's a lot of negative hype on that in terms of lack of devices, but it's just because it's new, right? And the as was already mentioned, the applications in manufacturing and logistics for something with this wavelength and this data rate and the flexibility are pretty substantial. And the other thing, to camp on something Ted was saying, I think in 6G, we need to assume that this is not the way the UEs are going to look, right? I hate to say it, but the smartphone is a mature technology, and we're going to see things evolve dramatically so that as they call it, the black rectangle may cease to exist as we know it, and the UEs will look an awful lot different, and it will expose use cases, some of which we've talked about, but in some cases ones we haven't thought about. And I'll also camp on one other thing. The largest moneymaker today in mobile communications is the mix of entertainment and advertising. And as it's not super glorious for us, but I don't think that's going to change much as we move past 5G into 6G, and there'll be just better ways of doing it.
You know what? I'm going to try and pull some questions in from the audience. I don't know if the panelists can see the questions as I can, but there's some related to the discussion. Actually, Roger, I'm going to put this one back to you. There's a question from Brett Carpenter saying, is IoT infrastructure a viable solution? I assume that means for sub-terahertz, or is that going to be relegated to lower frequencies?
So I think Michael and Amitava both, camped on this one immediately. From an infrastructure standpoint, cell density is a pretty big deal, and the ability to get better spectral efficiency for the last 100 years has all been about reducing the cell size. And the hardest part about doing that is backhaul. It's logistics, it's expensive, it's all the stuff that Ted mentioned. And so as soon as you mention the word infrastructure, that comes immediately to mind. So to get the data back from a busy cell site, it's great if you have access to fiber, but it just doesn't exist that many places, and it's pretty impractical and extremely expensive to install. And so I think that's a perfect example for expanding how we use this Internet of Things, whether it's an industrial or municipal or government or whatever approach. So I think absolutely.
Yeah, I think it's the aggregate of the data that's going to need to be transmitted. In Charlottesville, Virginia, just down the hall from us, we've got a company called Everactive that's making very low power IoT type devices to be used as monitoring of steam traps. Steam traps are ubiquitous in chemical plants, right? And it's an application where you take a sensor and you put it on a legacy industrial environment. And it's not each of the steam traps that is going to generate that terabits needing data, but the aggregate of those steam traps in a chemical plant will certainly be transmitting a lot of data. And then if you multiply that by other sensors that are laid on top of plants like that, you can see that there's going to be quite a need.
Yeah, I think quickly, I know we've been talking about backhaul a lot, but I think it's also front haul. That's that has the much higher requirements and really will enable densification of even lower bands, FR2, for instance, which has a very strict, high requirement, throughput requirement for wireless front haul. So it will allow for densification and more robustness for other deployments. And so that's one clear case, a use case I see for sub-terahertz early on.
I'm not going to jump to another question from the audience because I think it's a pretty good question for all of us to answer. And I'll read the question off and I'll bring it out. I'll leave it to the first person to volunteer to answer it. So the question from Shoaib on the on the questions here is, what would be the ideal regulation in terms of spectrum allocation to make terahertz become a reality, a swifter reality? So what can make it faster? If you had your magic wand and you could.
Yeah, I'll jump in. I'm sure
Okay.
Mike and others have ideas, but I think first of all, agreements by some of the major populous countries on what spectrum bands will be used for unlicensed and cellular access. If there's a global agreement on frequencies that are within a few gigahertz of each other, and they all open up, that will give the incentives to the device makers and the ecosystem that Gerhardt's talking about to finally start making commodity pricing mass quantity, because they know there's spectrum available in lots of countries, so they can export their products all around the world with one R&D investment. I think that's one of the main things. The other thing is I think taking advantage of the fact that as you get to these higher frequencies, you make these antennas much, much more directional on any kind of the link. And so regulatory clarity on what power emissions are in terms of EIRP with phased array antennas that can point anywhere and do very complex beam forming. And when I say beam forming, I mean forming narrow beams rather than the 4G beam forming, which is a DSP approach. If we make very, very narrow beams, we can exploit the directionality far above any perceived path loss, which is overblown in the minds of most engineers. So having EIRP regulations and safety items addressed, I think would make terahertz, sub-terahertz take off quick.
Thanks, Ted. Mike, did you want to add anything?
There are two situations. One, if you need less than 12.5 gigahertz, contiguous gigahertz, and the other is if you need more than 12.5. If you need less than 12.5, I agree with Ted. The key thing is picking the bands, because there are allocations there that give you at the moment up to 12.5 gigahertz. And if there was a consensus on such a band, that would get rid of the commercial issue. The problem is if you need more than 12.5 gigahertz, for instance, if you're trying to get hundreds of gigabits of data, which is possible in a backhaul situation, the only way to do that is to overlap the passive bands. And the allocations that were created at the 2000 World Radio Conference say that you can't do that until the passive and active community get together and agree on a sharing mechanism. So for any use that needs more than 12.5 gigahertz, there has to be a consensus between the active and passive community on a way to share. The technologies mentioned so far are ways to do that. There are some other possible ways to do that, but there's been a real traffic jam because of the two communities haven't been able to get together, and the regulators have had more apathy to let this traffic jam continue. But we need to either show that it's impossible to share or evaluate the mechanisms that would seem to enable sharing.
Okay, thanks. Oh, Dan?
Yeah, there was a question in the chat which addressed the issue of safety and limits. And I can just briefly comment on that. At the moment, to the best of my knowledge, there's no universally agreed sort of minimum, maximum exposure limit. People typically just extrapolate from lower frequencies using the IEEE standard. No, it's not a standard, it's a recommendation. I don't think there's actually any standard at these frequencies yet. So probably there ought to be at some point. I mean, I think I cannot imagine that would be a bad thing in order to encourage people to take this whole range of the spectrum seriously. From the point of view of the research community, there's been quite a bit of research done on this issue, and the answer appears to be, if it works at microwaves, then if it's safe at microwaves, it's going to be safe at terahertz too. The primary, as far as I know, the only agreed upon mechanism for a health risk is thermal. You can boil water with microwaves, you can boil water with terahertz radiation too if you have enough power. And so as long as you stay below thermal damage thresholds, you're fine.
There are standards, both European community and FCC on frequencies up to I think it's 300 gigahertz insert is one of them. And
Right. I
Yeah.
thought that was a recommendation, not a standard.
well, it's a recommendation by which they make their regulations. And
So bottom line is, in the future, we need more capacity. For more capacity, you need more bandwidth. And where do we get more bandwidth? You have to go to the sub-terahertz regime. As Mike said, that if you get 12 gigahertz of bandwidth, you can support 100 gigabits of data rate. And there may be some application which needs that kind of data rate, like any VR applications. So I think that is the mantra. You need more sophisticated applications of huge data rate. You need more bandwidth. Where you get more bandwidth, you go to different sub-terahertz regime. Of course, there is 14 gigahertz unlicensed band in the 57 to 71 gigahertz, which has not been utilized yet.
So maybe we'll move on to another question from the audience. And I think this comes from Andrew. So, and I think Amitava may have answered it a little bit there too as well. Does this frequency range have any advantages over 5 to 95 gigahertz, or what we commonly think of as FR2 in the 3GPP? And then I think further, are there any advantages for mesh networks or densification you see in the sub-terahertz versus the 95 and below?
The main advantage is you can certainly get 12.5 gigahertz that you can't get below 100. And if we solve the sharing problem, you get more than 12.5 gigahertz. Probably you can't get 100 gigahertz, but it looks plausible to get 40, 50 gigahertz with only sharing one passive band. And that's one way to do this. And while the emphasis has been on 5G and 6G, let me point out this country is wired together for other communication needs, mostly by fiber at the moment. There are parts of this country with high seismicity. And when California starts drifting off towards Hawaii, that fiber will probably snap. And we need a way to do quick repair for disasters like major earthquakes. Has nothing to do with 5G, or maybe a little bit to do with 5G and 6G, but 5G and 6G are not the only communication systems in the country. And one good use of this is for emergency repair of fiber networks till you have a chance to reinstall the fiber. If you break a piece of fiber with a shovel, you can repair it easily, but if you snap a whole bunch because it went across the San Andreas Fault, repair is not so simple.
Okay, thanks, Mike. So,
another one of the benefits above 100 gigahertz that some people often present as a downside is that you can actually be more inherently secure above 100 gigahertz than you can below 100 gigahertz, because you can tune exactly how far the radiation is going to go. And this brings up defense applications, and there's actually a growing number of defense applications. DoD is very interested in 5G. There's a lot of 5G test cases. Just recently in Microwave Journal, there was an article about Verizon cooperating with a base in Pearl Harbor to launch a 5G network there. And so I think we'll see more and more of that. I remember back I can't remember if it was the first Gulf War or the second Gulf War, there was an issue about getting flight plans over onto aircraft, and that you couldn't get the flight plan over onto the aircraft because you had to basically take a forklift of, or it wasn't the flight plan, but the bombing plan. You had to take a forklift full of paper onto the aircraft to get the bombing plan over. And so how was that solved? Well, it was put onto a computer or a tablet. But still tons of information. And if you can broadcast that in a burst with some secure type communication, huge advantage for the DoD type community.
Some other great applications that are going to be viable is as you get up to these super high frequencies, the hundreds of gigahertz, you can pick various molecular absorption bands that create massive attenuation, thousands of dB per kilometer, or tens of dB per couple meters, which means you're able to create what I've been calling whisper radios for some time. That is, you could have close range communications at super high data rate over several gigahertz of RF carrier but no one could hear it beyond a few meters because the attenuation of the atmosphere is so great. You could also use these frequencies to then replace electronic wiring or electronic buses in vehicles, tanks, ships, and operate with diversity wireless links that could be much cheaper and much lighter than the cables currently used. And with much lighter deployment of aircraft or boats or tanks, you then get a huge fuel savings where wireless would replace the wire and provide this covert operation with the rapid attenuation. There are a lot of things like that that become available that we could never think about below 100 gigahertz, let alone the fact that the antennas themselves will be very small, but very directional, which then yields other kinds of inherent safety, which Dan Middleman's published on over the past several years.
Okay, thanks. I think we've heard a lot of great answers on the advantages of above 95 gigahertz. I'm going to go to a question I have here is, so at the beginning, Roger talked a little about energy efficiency and our going to greater bandwidths and just transmitting more information and, you know, not necessarily balancing out. But the other aspect of this is there's a lot of challenges of power consumption at these higher frequencies. So we've got some single digit and low double digit PAs. What will it take to scale these semiconductor technologies for these applications? And maybe I'm going to give that to Ozge if he doesn't mind, because he leveraged the technologies from FR2. Is there anything on the horizon there, or what can we learn?
Yeah, so I think we started in an inefficient data point even in FR2, right? And you know, over them, I think we're working on the 5th generation of chips now, and the efficiency have gone up fairly high. But it also depends on the use case, right? So you know, when I give those numbers, I'm focused on the phased array integrated antenna modules that go into a UE or into something mobile. And that's a particular use case, of course, that has to be very power efficient, thermal efficient. But then there's also the front haul, back haul we talked about, and that can use a different solution, right? A different PA solution. It doesn't have to be as integrated or packaged, you know, like in a UE. So I think the numbers, you know, may start off low, but it just like in FR2, we'll get more efficient, and as the processes improve and the designs improve. So in that sense, I'm hopeful just from what I've seen in FR2.
Okay.
I think I could camp on that one too and say, you know, a really good example of, you know, what's the issue, right? If you could say, well, we're only going to do 100 gigahertz if we use exotic compound semiconductor technologies like indium phosphide and that kind of thing. There's more efficient up there. So is that feasible? Well, scaling indium phosphide production is pretty tough, right? There are just a number of boutique foundries out there, and they're pretty unique use cases. Well, that was true for gallium arsenide a long time ago, and it was very true for GaN not so long ago. And GaN became usable and affordable with a vast expansion of base stations that were developed in 4G. It was driven by a lot of work in China. And all of a sudden, scaling GaN production for the sake of power amplifiers became, you know, a much bigger, it drove the price down. And then there's new technologies that have been developed even for GaN to make it work a lot better. It had a lot of problems, but different substrates and different epitaxial approaches for gallium nitride made a pretty big difference in its performance. And I think, you know, that's the challenge that's in front of us from a research perspective is to build scalable technology and, you know, to drive higher frequency capabilities in silicon and maybe less expensive technologies as well. But you can just see this evolve in some pretty amazing ways over the last few years. And the scaling issue is one of those things that hopefully we could take advantage of as these things catch on, like those previous examples.
Great.
Yeah, and we've got this new CHIPS Act that is trying to spur a lot of semiconductor development in the United States. And it's not only intended to reshore silicon type activity, but to continue to advance new technologies, and not only new basic semiconductor technologies, but packaging technologies. You know, there's been a lot of focus in the research community over the past couple of decades on heterogeneous integration. And that certainly has an application in mixed signal wireless ICs going forward, where you can take chiplets and put them onto silicon, and can certainly be a place where the US can take a manufacturing leadership role worldwide.
Great, thanks. I'm gonna pop back to some questions from the audience, and I think there are two questions out there that talk about what kind of formats are we going to use over the air. I think one talking about modulation. So, you know, are we simply, the way I read it maybe could be, are we simply going to scale 5G FR2? Can we scale 5G FR2? Are there better alternatives there? And then if we can branch out after that, do techniques that we use in FR2 and FR1, like coordinated multipoint, would they be a good fit in this, or are they absolutely needed for the densification? So who would like to go first?
Yeah, I'll take that first, Andrew. Good question. We give away a lot in PAPR and back off in our amplifiers. We give away several dB, which is a lot of waste of power. And the reason why we do it is because 4G evolved in the lower frequencies where the wavelengths are large and the antennas have relatively little directionality. So there's a lot of multipath, and the brilliance of LTE and OFDM is that it's a bunch of narrow band flat fading channels, which is where you get maximum capacity from IMO when you're really fading. But as you move up to these higher and higher frequencies, where you can make the link more like a frozen rope in the air with less multipath and less fading, I think we're going to have to change modulation formats over the next decade to something that doesn't give up that huge power loss in having to do back off on the amplifier. I think we're going to have to figure out ways to maximize every bit of power and battery, because as Roger said, it is more efficient 5G over 4G in joules per second. We have a paper coming out in the IEEE Wireless Communications magazine developing a new theory and a new parameter called the waste factor, which can be applied to any system, any link, any modulation, any end-to-end communication. The waste factor will determine as a metric how much power you're giving away. And I think we're going to change modulations to take advantage of these very directional channels as we go up to sub-terahertz.
Yeah,
that's my opinion. I don't know if others agree.
I agree.
So we have been looking at various single carrier modulation for a long time, and there is an advantage with PAPR, and especially in these higher bands where we have this. So the single carrier modulation is very viable. So a couple of questions we have to ask with single carrier modulation. We say PAPR so we can increase the uplink coverage or generally coverage, but you can't do carrier aggregation. Once you do carrier aggregation, you lose the single carrier property. So as Mike said, that if you want to aggregate multiple band, you will lose the single carrier property. Having said that, so if you look at the application of sensing and communication, because the free path loss in radar is to the power 4 compared to the power of 2 in communication. So how do you design a waveform which will serve both the needs of communication and sensing? So that's one aspect you have to look at, or you design a separate waveform communication and separate waveforms for sensing. So these are all the research questions we have to address during the sub-terahertz, when we are addressing the sub-terahertz regime.
Again, I saw you nodding.
Yeah, I expect Joseph Jonet is probably in the audience here. One of Joseph's favorite points to make is that there appears to be no consensus on what waveform will be used in 6G. And I think that's he's making a good point, which is that there is no reason at all to assume that it's going to be the same. And in fact, given the channel and given the lack of multipath and the water absorption resonances and so on, there are tremendous opportunities for designing different types of modulation formats to take advantage of the sort of unique aspects of this system. There's no reason to believe it'll be the same.
Very good. So we've touched on modulation. I think pointing out that there's huge opportunities for reducing PAPR and new types of applications. But what about the MIMO aspect? Is MIMO going to be the same at sub-terahertz, or are we going to use coordinated multipoint, or is it going to be different? Any thoughts on that to answer Shoaib's question?
Yeah, we studied comp at 73 gigahertz about 6 years ago. Did a lot of channels and capacity prediction. You don't get a whole lot of advantage in comp other than the basic diversity of location, and that diversity is going to be solved by densification. So densification is going to solve a huge amount of capacity problems, and it's also going to solve a lot of, I think, the signal processing issues as antennas become more directional. Certainly, we're going to have, I believe, massive MIMO. There's a lot of sense to massive MIMO, and you can kind of do that with a lot more antenna elements, creating separate channels. And that's where we're going to get the capacity. The fact that the physical footprint of these antennas, of these panels in the cellular world, will have orders of magnitude more antenna elements. And those antenna elements will allow us to do massive MIMO and get big capacities. So I think that's how the world will switch as we get these wider bandwidth and larger number of antennas in the physical area.
Yeah, I think one of the challenges with things like coordinated multipoint is you're talking about, if you're going to do that at this frequency, you also have very wide bandwidths, and the channel state information, getting the information coordinated between the multiple points requires a lot of data to move around very fast with low latencies, and it might not be worth it. As Ted, as you suggest, right? You might be better off with cell density and other ways. Comp might be a lot more valuable down in FR1 than anything else. And then I'd say from a MIMO perspective, I've seen very little truly massive MIMO research done at frequencies above 20 gigahertz. In fact, there's only one institution I know of that's actually doing this. And so I'm really anxious to see that evolve, especially given that the channel is not very rich, right? There aren't a lot of reflective paths where massive MIMO is something you can really take advantage of. So far at these higher frequencies, what I see is mostly use different polarization for MIMO techniques, but it's up to you, Ted, to figure out how to make that more massive. I'm anxious to see how that's going to work, because I have my doubts.
Yeah.
Well, the massive is going to be in the digital signal processing to allow the orthogonalization in a better behaved channel using all these massive antenna elements. So it's going to be a little different, I believe, than what we do today, but we're on the right path with massive MIMO being deployed at midband by T-Mobile, I think.
But in this regime, I think millimeter wave and sub-terahertz, SU MIMO, you'll not get more than 2 to 4 streams, especially if you're line of sight, right? So you'll not get, the most of the advantage will come from how efficiently you're using mmWave, not SU MIMO. So SU MIMO dictates the peak rate, and you can see with 2x2 MIMO, with 12 gigahertz of spectrum, you can easily get 100 gigabits of data rate, and with 256 square modulation. So I think we have to focus on mainly mmWave, not SU MIMO at this regime.
So I think also as you densify, I think the multi-TRT aspect is actually more important. So, because you'll densify with whether it's IAV nodes or RIS and remote radio heads, being able to switch from those transmission points to maintain some robust thing. So it's more than just densifying, but being able to switch between transmission points. That would be key.
Yeah, because one of the key things is the blockage is the main problem at this frequency regimes. And to avoid blockages, as I've told, you have to have line of sight to multiple base stations, which Oskar is saying. And we have to make sure the topology and densification is such that the UE has always visibility to multiple base stations.
When one talks about MIMO, the first thing that comes to my head is, what Ted talks about, these arrays of many, many, many antennas. And of course, the first thing I think is, wow, that's a serious fabrication challenge. Not that it can't be overcome, but it's not something that I'm aware of people having built many examples of. On the other hand, nowadays there are, and I don't know if you may be aware of this, there are terahertz cameras, which are, again, multi-pixel focal plane arrays with, thousands of elements in some sort of square array, kind of wavelength scale elements. And so, that's a step along the path. I mean, that's at least encouraging evidence that it's feasible.
Okay, so I'm going to come to maybe a tougher question here. I think there's been some talk about some skepticism about using these communication frequencies above 100 gigahertz. I think we've touched on this a little bit before in some of the answers, but this is in the context of 5G FR2, so the sub 95 gigahertz, not necessarily being the widest supported, most successful at the moment. So what are your perspectives on that skepticism, and what will it take to realize usable systems at these frequencies? What impact does that have? Anyone want to take that on first?
So the very first long distance microwave communications link was 1931, and it wasn't for at least 20 years before they started becoming widely deployed. So to those people who are skeptics, the first thing I would say is be a little patient. We're really right at the beginning of this game. Calm down. It'll get there.
Okay.
I'll even take you back to the 1800s, the late 1800s, with Lebedev and Bose in Russia and India, which we talk about in our millimeter wave book. They were doing 60 gigahertz communication back then.
Yeah, I mean, I think, I hope it's not 20 years. That's puts us at
Yeah.
70.
I was 20 and 100 is what I heard. So I'm not sure.
See, at universities, we have long time horizons. I apologize.
I mean, really, we're in 2022. Right? We have 8 more years of 5G, so we're at the beginning of the deployments. The millimeter wave, even the spectrum allocations are happening around the world even this year, where Brazil, Spain, those are all coming in this year. Many operators have been sitting, waiting for the ecosystem to build up, and I think the ecosystem is building up from the likes of Nokia, Ericsson, and also the repeater companies, and there's a big ecosystem developing, and even RIS companies or passive RIS companies. So the costs are coming down, the options are there, the optimization, cost optimization of deployments is getting there. And I think it'll start off slowly in targeted areas, just like Verizon is doing in stadiums and hotspots, and before it gets to a bigger level. But I certainly expect by the time we're deploying 6G that there'll be significant FR2 deployments, and then in 6G it'll just be a given that FR2 is there for capacity.
Yeah, I agree.
At the risk of sounding like a broken record, let me point out, if you want more than 12.5 gigahertz, this is not other technologies with minimal regulation. This is technology which has a lot of baggage that was started to build at year 2000.
Mike, I think for the audience, maybe you should just tell them how you get that 12.5 gigahertz.
I don't participating in ITUR discussions, and the framework that's been adopted in both WRC and the ITUR at the moment, I think, has at least a 10-year lead time. So I don't think if we all decided today we needed wideband systems above 100 gigahertz, that the ITU morass that's been created will take at least 10 years to solve. Maybe if governments start lighting a fire under ITU, it could be faster. And I know today we have a new Secretary General of the ITU, the first woman in history. But the point is, as opposed to other technologies, there's an awful lot of regulation standing in the way of bandwidths greater than 12.5 gigahertz. And we have to recognize that and address it in parallel with the pure technical issues.
Maybe one last follow-on question, then I'll try and summarize. So to the panel, so Mike was talking about 12.5 gigahertz and larger bandwidths. Do we need that to make sub-terahertz successful? Do we have to wait for that regulation, or can we do things without that bandwidth? Any thoughts on that? Or it doesn't differentiate itself?
Well, I mean, I think that the research can be ongoing and the proof of concepts can be ongoing in the laboratory type setting. And certainly, there's the 21 gigahertz of bandwidth and 4 bands above 95 gigahertz spectrum horizons put out there. Things like the integrated sensing and communications can be explored. We're talking, we're still early on in millimeter wave, and we've got 10, 15 years to go for sub-terahertz deployment into some 6G type system. And so there's a lot of runway there still, and there's time. I mean, there's not time in the sense that Mike's talking about, that the ITU regulations need to get figured out, but there's time in terms of getting the development done, getting the research done.
Yeah, so if we want to recreate the holodeck, we need this kind of data rates, right? Huge, 100 gigabits of data rate. And that's the only way, the spectrum regime above 100 gigahertz, where you can get that bandwidth. So it is the use cases. And I want to see some parts of the holodeck in the next 10 to 20 years.
I'm with you. Yes.
Yeah,
I think the other thing is, go ahead, Ted.
No, go ahead, Roger.
Well, I was just going to say so 12.5, I agree with Mike, right? We got to work with the regulatory world to figure out how to expand that, because contiguous spectrum is important. And the only other place that has that kind of contiguous spectrum is the 14 gigahertz that's all unlicensed between 57 and 71, right? But that's got the unlicensed, issue kind of wrapped around it. And I think so 12.5 is a lot more than we have anywhere else. And getting started in that space is it may not be sufficient, but it is absolutely necessary.
The unlicensed part also has very high atmospheric absorption, which is one of the reasons why it's unlicensed.
Exactly, right.
I just follow.
My gut feel is we're going to need more. We're going to need to give
All right.
4 carriers in any country 5 gigahertz to 10 gigahertz. We're going to need more than 12.5 gigahertz contiguous, I think.
Okay, so we need the bandwidth, I hear. With that, we've come up on the end of the hour. I think we've had a great panel today. I'd like to thank all the panelists for participating. We had a great discussion of use cases and the advantages that we can have above 95 gigahertz with this very large bandwidth, opportunities for new innovation in terms of modulations for different types of applications, both for radar and for lower, more power efficiency. We've heard positive statements about the opportunity to innovate on devices and address energy efficiency. Really exciting discussion today. Again, my thanks to the audience for the questions that have come in, and thanks to everyone for participating today.
Thanks, Mark.
Thank you.
Thanks,
Thanks,
Mark.
Thanks,
Thanks, Mark.
Good to see everyone.
Bye.
See you.
Bye.
Bye.